In this video I'll be going through the thermal physics part of Unit 5, that should be, I'll just correct that at the top right now, Unit 5 of Edexcel A2 Physics. So this covers the ideas of heat, temperature and specific heat capacity, the idea of kinetic and thermal energy, and the equations related to the ideal gases and the kinetic theory of gases. So in terms of the explaining everything task, it's pretty straightforward. We need to describe kinetic theory of gases using, or kinetic theory of heat, I guess would be a better phrase for it, using equations where appropriate. So the key thing to really do is to link the idea of kinetic energy and thermal energy and say that they're linked and give the equation by which they're linked, which I'll show you in a second. Also, the idea of in here is a root mean squared, but the mean squared part of it is key, as that's part of the equation that links kinetic and thermal energy. The final part of this is sort of talking really about internal energy. And you've got to remember that internal energy is the energy inside a system, not necessarily of the system as a whole. It's not to do with it's not to do with the outside of the object. So if we take this calculator as a box, the internal energy would be the energy the particles have inside of there as they move around, not any kinetic energy that this box has by it moving. Okay, or any potential energy it has because it's above the ground. It's all to do with what's actually happening inside the system. So that's what we mean when we talk about internal energy, energy that's happening inside the system. So in terms of the equations that are key for this area, you've got the idea of E equals mc delta theta to do with specific heat capacity, but this is the one to do with kinetic theory, where you've got the half m mean speed squared, the mean of the squares of speed, is equal to 3 over 2 kt. Okay, so that's one of the main equations. Just spotted that there's one of the main equations that is not mentioned, that is mentioned next on this list, but isn't related to moles. That's the ideal gas equation. So occasionally you get it mentioned in terms of moles, but don't overly worry about it. They'll guide you through it if they do. There's a question in the ISP based around it. It was generally just on the old spec and not so much on the new spec, although I do like to still go through it because I know there's a lot of people that do chemistry and physics together. So in terms of moles, that's what you get. So all that's actually happened is that K has been multiplied through by Avogadro's constant. So that's has given us this new value of R instead, but R has a value of, I think, if I remember correctly, I'll double check in a second, 8.31. So that's the only difference between these two. That's the other constant before, that's going to be 8.31, and that's the number of moles. I'm pretty sure it's 8.31. Right, I think the next part of the explaining everything task was talking about specific heat capacity. Yep, there it is. So to describe how to calculate the specific heat capacity of a liquid, so remember you've got to use the equation of E equals mc delta theta, and the idea is that if you increase the temperature of a specific mass, so of a certain liquid, and you've got a specific mass of that liquid, you can figure out how much energy has been delivered to it. Now remember, energy is equal to power of, power is equal to energy over time. So what you could actually do is to figure out how much power your heating source has. If it was an electrical heating source, you could do a P equals IV calculation, and then you can figure out how much power you've actually delivered, and then compare those two things, compare those two powers, and from that comparison you can figure out the efficiency of your heating method. Okay, let's get stuck into some questions now. Let's move my sheet over. Where are we? Right, okay, first question. A valid set of units for specific heat capacity is, okay, well, here's our equation for specific heat capacity. I'll write it out again down here so we can see it. E equals mc delta theta. We want units for specific heat capacity, so we need to rearrange for C. So that's E over m delta theta. So that's going to be joules That's going to be kilograms, and that's going to be Kelvin. So joules, per kilogram per Kelvin is what we need. There we have C. It's given us joules per kilogram per Kelvin, so it's C. Next, what is meant by the absolute zero of temperature? What is meant by the absolute zero of temperature? Well, absolute zero is where the pressure inside of a gas, so inside of a volume of gas, is zero. So the pressure, water volume of the gas is zero. Or it could be at which the kinetic energy is zero. So either of those 2 points is valid. So mentioning kinetic energy is zero, or mentioning that the pressure is zero. If you're going to go with the energy route, you have to mention kinetic energy. You can't just say energy, you have to say kinetic energy is zero. So next question talks about football, in terms of the fact that footballs need to have a maximum volume and maximum pressure, and it needs to be a certain maximum above atmospheric pressure. So it needs to be 1.1 times 10 to the 5 above 1 times 10 to the 5. Assuming, and we're assuming the fact that the thickness of the ball is negligible, that the air inside is at temperature 10 degrees. That's pretty cool when you think about it. But then football is played over the winter months for the majority of the time, so that makes sense. So the maximum amount of air inside the ball is about 0.5 moles. Okay, so this is the question I was talking about before, in the fact that it's done in terms of moles. When we look at our equations from before, that's the equation we're going to use because it tells us the number of moles. So we want this equation in terms of N. So a simple rearrangement gives us PV over RT is equal to N. So N is equal to PV over RT. Well, P is our pressure, so we need to add together our 1 and our 1.1 times 10 to the 5. So 1 times 10 to the 5 add 1.1 times 10 to the 5 is equal to 2.1 times 10 to the 5. That's pretty straightforward. That's our pressure. We need to add them together because it says it needs to be 1.1 above atmospheric. The volume they've given us is 5.8 times 10 to the minus 3. We then need to divide that by 8.3, which is our constant R there, our gas constant as it's known. And we need to multiply that by temperature. Now temperature needs to be in Kelvin, so it's going to be 10 added to 273, so it's 283. Okay. If you whack that through your calculator, you should end up with something close to 0.5. About 0.52 is what I've got previously. I'm just going to double check that right now. 1.2 to the 5 times 5.8 minus 3 divided by 8.31 times 283. Yeah, about 0.52 is what you end up with. Brilliant. 1 mole of air has a mass of 1 mole of air has a mass of 0.029. Calculate the maximum mass of air allowed inside the ball. Well, you just need to multiply 0.029 by 0.52, and that's going to give you the maximum mass of air. So it's about 0.015 kilograms is equal to 0.015 kilograms. So that's going to be that'll be 100 kilograms. That'll be 100 grams. Sorry, that would be 10 grams. It's about 15 grams of air. Now that doesn't sound like much, but remember it's moving around there with a high pressure. So therefore, it means the ball is fairly tense. A football is also required to have a minimum pressure of 0.6 times 10 to the 5. There we go. There's a high pressure above atmospheric pressure. So it's going to be 1.6 times 10 to the 5 is the actual pressure inside, because remember it's above atmospheric. Assuming the volume of the ball remained constant, calculate the lowest temperature to which the air inside the ball could fall while meeting the pressure requirements. So we know that P over T is constant. We know that P over T must be constant. The reason why P over T must be constant is because volume is remaining constant. So P divided by T must be a constant. So the pressure before divided by temperature before is equal to the pressure afterwards divided by the temperature afterwards. Okay, that's the idea that we're using. So it's a 2 and that's a 2. Right. So let's work this through. We know the pressure before. We know the pressure before. We know the temperature before. We know the pressure afterwards. We know the temperature afterwards. So we want the temperature afterwards. Let's rearrange for that temperature afterwards. So what you actually end up with is P2 over P1 times by T1. That's just a rearrangement of this expression here. And then you put your values in. And remember, this is going to be your 2.1 times, sorry, this is going to be your 1.6 times 10 to the 5. That's going to be your 1.6 times 10 to the 5, 2.1 times 10 to the 5, and that's going to be your 10. Okay, so it's 1.6 times 10 to the 5 divided by 2.1 times 10 to the 5 multiplied by 10. She should end up with somewhere in the region of about remember, sorry, you should do it in Kelvin, not multiplying by 10. That's a mistake for myself. By 10. So let's put it into Kelvin. So it's going to be 283. She should have been something in the region of 215 to 216 degrees. There you go. Okay, so the biggest mistake is the mistake I said the first time as I was about to type my numbers in. That I said was 10. That is not 10. That's 283. Remember, all calculations in this need to be done in Kelvin. Right. Next question. Common question: definition of specific heat capacity, and also another common question explaining the term internal energy. So let's go for both of those one by one. So in terms of a specific heat capacity, it's the energy required when a kilogram undergoes a temperature change of 1 degree. Okay, so it's the energy required to raise 1 kilogram by 1 degree, to raise the temperature or to change the temperature. Okay, or I would say change the temperature of 1 kilogram by 1 degree. Internal energy, well, internal energy is the sum of the molecular or the atomic potential and kinetic energies. It's all of the potential and all of the kinetic energies of the molecules, not of the system, of the molecules. Don't say particles, and don't say gravitational potential. Okay, remember to say it's the sum of all the kinetic and potential energies of all of the molecules, of all of the atoms. Okay, so we've got a night storage container here with a stack of bricks. It's warmed in the night by electric power and gives off its energy during the day to the room. Heater normally has bricks coming together of 800 kilograms. Calculate the energy given out by this as it cools from 10 to from 70 to 20. Okay, so equals MC delta theta. That's what they want. 800 is that. You've been given a specific heat capacity. And you'll be given a temperature change of 50. Remember, that'll be 50 degrees or 50 Kelvin, it'll be the same. So you put those values in. Three, 4, 5, 6, 7. It's 4.4 times 10 to the 7 joules. So remember, they could say, oh, this happened over 20 hours. What is the power rating of this device? And then you just divide that by the number of seconds in 20 hours. But they're not doing that in this question. So question 4. So we've got a pressure against 1 over volume graph, often mistaken. The measure was taken of pressure exerted and its volume. The graph was plotted. Okay, so state in words the relationship represented by this graph. So pressure is directly proportional to the inverse of volume, or pressure is inversely proportional to volume. That's the main thing. So as pressure increases, volume decreases. Pressure is inversely proportional to volume. Is the main thing you've got to state in there. On the axes below, sketch a graph that would be obtained if pressure was plotted against volume. So it'll be going the other way. Okay, it'll be going the other way. So have a negative gradient. Right, the ideal gas law is PV. The ideal gas law is PV equals nRT. Okay, so that's what I discussed, where R is to do with the gas constant, not K, which is the Boltzmann constant. Show that PV has the same unit as energy. Okay, so PV having the same units of energy, so P, pressure, has the unit of pascals, and volume has the units of meters cubed. What a pascal is a Newton per meter squared. Let me just lift this sheet up. There you go. Newton per meter squared. If you don't know if you don't remember that, there's a horrible joke that you can look up that links a pascal and a Newton per meter squared. And we want to show that that has the same unit as energy. So energy, work. Energy is work. So work is equal to force times distance, which is equal to Newton meter, Newton times meter. So if you multiply these through, you end up with Newton meter. And you can see the units are equivalent there. Explain in terms of the kinetic model how molecules of a gas exert pressure. You may be awarded a mark for clarity of your answer. So it's a 5-mark question. Okay, it's a tricky question to get all 5 marks on. And there's generally 4 points for this. So the 5th mark is about the quality of your actual answer. So I'll show you the mark scheme for this because it shows it very clearly the sort of things that they're actually after. Right, here we go. So here we go. Molecules collide with the wall of a container. So we know that whenever there's a container and molecules hit the edges, okay, that's what we call pressure. That pressure is exerted because there's been a force, and the force arrives because there's a change of momentum. Okay, so remember that force is the rate of change of momentum. Force is equal to change in mv over t. So t over t makes it a rate. The fact it's over t makes it a rate, it's a change in mv. So it undergoes a change in direction and therefore undergoes a change in momentum. So when its pressure is equal to this force divided by the area it actually acts over, and a large number of molecules are actually involved in these collisions, and hence the pressure is the same or it's constant throughout. Right, let's have a look at question 5, which is the final question on this ISP. So we've got apparatus here that allows us to investigate pressure and volume. Okay, so it allows us to investigate the relationship between pressure and volume. So this is Boyle's law apparatus. So we've got the temperature of 22 degrees. The volume is 30 centimeters cubed. When the gas pressure is 200 times 10 to the 3. Calculate the pressure exerted by the gas when the volume decreases by 50. Well, we know that pressure times by volume must be equal to a constant. Okay, we know that temperature is constant in this. So if you think about nRT, N is constant, R is constant, T must be constant. Or if you think that PV equals NKT, N is constant, K is constant, T is constant. I've told us it's 22 throughout the experiment. So we must know that PV multiplied must equal a constant. So what we can say is if we know the pressure beforehand and the pressure afterwards, so if we know the pressure beforehand and the volume beforehand, and we know one of the variables afterwards, we can figure it out. So the idea is that P1 V1 is equal to P2 V2. So our pressure beforehand we've got as 200 times 10 to the 3. Our volume beforehand we have as 20. Doesn't matter about the units as long as they're consistent. Oh, actually, no, the units will cancel, so it's fine, yeah. The pressure afterwards is what we want. The volume afterwards, it says when the volume decreases by 5. So if it's decreased by 5, that's going to be 15. Okay, so our numbers are going to be 200 times 10 to the 3 pascals times 20 centimeters cubed is equal to pressure 2, and then we know volume 2, but it's been multiplied here, we might as well divide it over here, so that's going to be 15 centimeters cubed. So if you put those numbers through, it's quite obvious the pressure is going to increase because the volume is decreased. Okay, so due to the fact the volume is decreased, the pressure is going to be larger, and the value you should get is about, let me just figure out this number, 2,606, so 266,666.63 Kelvin. Okay, right, just a nice question to get to start us off. The volume of oil has a cross-sectional area of 7 times 10 to the minus 5 meters squared. Calculate the force. Well, we know that pressure is equal to force over area. So force must equal pressure times by area. Pretty straightforward. Okay, so you've got your pressure here and you've got your area here. The student draws a graph. So a student draws a sketch of her results and obtains the following graph. She correctly uses the pressure law to calculate the pressure exerted by 20 centimeters cubed of gas at 30 degrees Celsius. What value does she obtain? Well, the pressure law essentially is telling us that, well, we've got values of pressure and temperature, so it must be pressure over temperature. The values is the relationship that we're using, and we know that's equal to a constant. So that's the pressure law. Remember, you need to convert the temperature to Kelvin. So just like before, pressure before must equal to pressure afterwards. You sub in the values that you have. And she wants the value of the pressure, and you should end up with about 208,813 or something close to that. Remember, there is a difference in temperature that we've got to use here, with one being 108 Kelvin and the other one being 295 Kelvin. Use the axes to sketch a graph a student would have obtained had the gas been at this higher temperature. Okay, so it's going to be similar to this one. Okay, but it's going to be above beforehand. At the end, it's going to be very similar. Okay, but at the start, there's going to be a higher pressure due to the fact there's a higher temperature. It's going to be above beforehand, but it's going to have a similar curve, similar shaped curve. So above all the way with a similar shaped curve. And that brings us to the end of ISP Task 2 on thermal physics.